Imagine a world where a cat can be alive and dead at the same time. A world where a particle can be here, there, and everywhere simultaneously. A world where reality itself refuses to decide until you look at it. This is not science fiction. This is the world of quantum mechanics. But here's the puzzle. If the quantum world is so strange, why doesn't our everyday world look the same? Why don't we see chairs in superposition, or cars existing in multiple places at once? Why is it that quantum weirdness seems to vanish the moment we step into the macroscopic world? This mystery takes us into one of the strangest and least understood concepts in physics: quantum decoherence. To understand decoherence, let's first step back into the bizarre playground of quantum mechanics. Imagine flipping a coin into the air. While it spins, you might think of it as undecided. Not heads, not tails, just waiting to land. But in quantum mechanics, the coin is not undecided. It is truly both heads and tails at the same time, a state called superposition. Only when it lands, or when you look at it, does it appear as one definite outcome. Physicists call this superposition, and it challenges everything we believe about reality. Erwin Schrödinger captured this paradox with his famous thought experiment: the cat in the box. Inside the box, a radioactive atom may decay or may not. If it decays, poison is released and the cat dies. If it doesn't decay, the cat lives. According to quantum mechanics, until you open the box, the atom is both decayed and not decayed, which means the cat is both dead and alive. A creature suspended between life and death in a ghostly superposition. But when you open the box, the cat is either dead or alive, never both. And here lies the mystery. If the rules of quantum mechanics allow for cats in superposition, then why don't we ever see them? Why does reality always seem to collapse into one version of events? This is the heart of the measurement problem. When scientists talk about measurement, they don't mean just human observation. Measurement in physics is anything that forces a quantum system to choose. A particle is like a fluffy cloud of possibilities, but once you measure it, it snaps into a single outcome. The mystery is why. Does our act of looking force reality to decide? Does consciousness play a role in collapsing the wave function? Or is something else at work? This is where decoherence enters the story. Decoherence doesn't rely on human eyes or minds. Instead, it says that quantum systems are never truly alone. They are surrounded by an environment: air molecules, photons of light, vibrations of heat, countless invisible interactions. Each tiny interaction is like the universe peeking into the box. Each little nudge leaks information about the quantum system into the environment, and the more the environment learns, the faster the quantum fog disappears. Think of a coin balanced on your finger. In a perfectly silent, dark room, you could keep it spinning, mysterious and undecided. But now, imagine turning on a fan, filling the room with noise and shining bright lights. The coin is disturbed, nudged, rattled, until it falls one way or the other. That's decoherence. The environment is like the noisy crowd that refuses to let the coin remain balanced. Nowhere is this clearer than in the famous double-slit experiment. Fire particles like electrons at two slits, and they don't behave like particles at all. They form an interference pattern, like waves overlapping, as if each particle went through both slits at once. But the moment you try to detect which slit it went through, the wave pattern vanishes. The electron behaves like a simple particle again. Decoherence tells us this doesn't require a human observer. Even if no person looks, a stray photon bouncing off the electron counts as a measurement. The environment itself is constantly collapsing the experiment, forcing particles to behave classically. This is why we don't see quantum weirdness in everyday life. Electrons, atoms, and photons can be isolated well enough in a lab to stay quantum. But bigger objects like cats, humans, or chairs are constantly bombarded by photons, air molecules, and thermal vibrations. The environment interacts with them so intensely that superpositions vanish almost instantly. Decoherence happens unimaginably fast. By the time you could even imagine a cat being both alive and dead, decoherence has already forced the cat into one outcome. Imagine a whisper in a quiet room. In silence, you hear every delicate vibration. That whisper is like the fragile quantum world. But place the same whisper in a crowded marketplace and it disappears instantly into the noise. That's decoherence. The larger and noisier the environment, the faster quantum superpositions dissolve into classical certainty. But here's the catch. Decoherence explains why quantum weirdness vanishes, but it doesn't fully solve the measurement problem. It tells us how superpositions spread into the environment, but it doesn't explain why one outcome becomes real instead of many. In other words, decoherence describes how quantum possibilities disappear into the noise, but not why you, here and now, see only one definite version of events. Physicists have tried to answer this puzzle with competing interpretations. The many worlds interpretation says that nothing really collapses. All outcomes happen, but in separate universes. When the cat is both dead and alive, decoherence just separates these branches, and we find ourselves in one branch or the other. Collapse theories argue that something real happens. Some physical process forces the wave function to collapse into a single outcome, though we don't yet know what. Some argue consciousness plays a role, that our minds somehow force the collapse, though this idea is highly debated. And then there's quantum Darwinism, a newer idea, suggesting that the environment acts like natural selection. Out of all possible realities, only certain stable outcomes survive long enough to be shared, recorded, and agreed upon as real. So where does this leave us? Decoherence is not the end of the story. It's only the beginning. It explains why the quantum weirdness is hidden, but not why reality chooses. Every breath you take, every photon bouncing off your skin, every sound wave that reaches your ear, is a reminder that the classical world you live in is not fundamental. It is a shadow, a stable mask born from the fragile fog of quantum possibilities. And maybe one day we will truly understand why the universe chooses the path it does. Maybe one day we'll know whether we collapse reality or whether all realities exist side by side, invisible to us. Until then, we remain travelers in a world half seen, half hidden, a world where the line between quantum and classical is blurred, and the mystery of existence remains unsolved. If you enjoyed this journey into the hidden layers of reality, make sure to like this video, share it with those who wonder about the universe, and subscribe to Beyond Newton. Because the cosmos is far stranger than we ever imagined, and together, we're going to uncover it.